Hello everyone. So today, one second. Today let's solve the problem dividing kingdom 2. Right. So this was asked in the Codeforces around 360 for the division 1. Right. So let's see. You can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So let's see what the question states here. Now, yeah, we have n cities. We have been given n cities and m numbered roads. Right. So we have been given n cities and m numbered roads, each with a length w, each with a length w. Right. For the query l comma r, nothing but the left and right. For the query left to right, basically for the query left to right, only roads with the indices left to right, nothing but L to R remain. Only roads with the indices L to R remain. L to R remain. Right. So we must partition cities into two groups. What we have to do? We must partition cities into two groups. Right. So we must this one. What do we call? We must partition cities into two groups just to minimize the maximum length of any road whose both endpoints lie in the same group. This one whose both endpoints lie in the same group. Whose both endpoints lie in the same group. Right. So we must um, partition cities into the two groups to maximize the maximum to minimize the maximum length of any roads whose endpoints lie in the same group in the sense hardness, in the case of hardness, right? If it is possible to partition so that no remaining road has both endpoints in the same group, uh, I mean, yeah, if it is impossible, right? Sorry, yeah, if it is possible to partition so that no remaining road has both points in the same group, then we have to return -1. Then we have to return -1. If we are given q queries, we have to print the minimal hardness for each. Minimal hardness for each, or we have to print the minimal hardness for each, right? So I'll just read this one out loud so that listen to this carefully so that we understand this one correctly. We have n cities and m numbered roads, right? For the query left comma right, L comma R, this one only roads with the indices L to R remain. L to R. So this one will remain. Only roads with the indices L to R remain. We must partition cities into two groups. We must partition cities into two groups, right? Um, we must partition cities into two groups to minimize the maximum length of any road whose both endpoints lie in the same group, right? If it is possible to partition so that no remaining road has both endpoints in the same group, then answer is -1. Then the answer is -1. And we have been given q queries. In that case, we have to print the minimal hardness of the each. If we are not able to partition, then we have to print the minimal hardness for the each. Minimal hardness for the each. So this is the question basically, right? So let me delete this one. Let me come to the input output, right? So this is fine, I believe. Yeah. Now see here. Now we have been given L equals. So suppose consider this one. So among this one, let's consider first one, right? First example, this one, first edge basically. So this is the first edge they have given in the question actually, right? 3, 5. This is nothing but L and this is nothing but R accordingly with the question that I have read, right? So edge indices here are 3, 4, and 5. Edge indices are 3, 4, and 5 respectively, right? Edges here we can just go with the edges in this way 1, 2, 3. So basically, yeah, 1, 2, 3, and weight will be basically 38. The first one, see here, this one, this they have given, right? So then we have to go with 2 to this one, 2 to 1 weight. So basically 33, as well as this one, 2 to 4 they have given right here. This one, and this one. 2 to 4, this is fine. 2 to 4, we have been given weight equals 28. Weight equals 28. These three basically, right? So we can't go with 2, 3, this one with a weight 40, right? So this one, we can just go with a 38, 33, and 28, right? For the edges 1, 3, 2, 1, as well as the 2, 4 with the this one, edge 3, 5, as we are going with only the this one. The answer that we need to get here is -1. So same thing goes with other edges as well, right? So let's consider the same example, man. Let's consider this one, this edge basically 3, 5, and we need to get the answer -1, right? Also, let's consider second one as well, right? Let's see. So I hope the input output part is completely clear here, right? So what they have given, yeah. Now let me delete this one. Now I hope the question is completely clear along with the approach and the uh, along with the this one input output. Now let's do one thing. Let's discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. Just give me a second here. So I have considered the same first example that they have given in the question, right? So we'll be considering this one. Basically, it's 3, 5. Let's go with 2.26 as well if I have time, right? So this is fine, man. The output that we need to get here for the whole this one input -1, 33, -1, and 33. So this is fine. Now let's do one thing. Let's go with a step-by-step explanation, right? So I just want to tell you one thing, that we will be making use of the DSU, or the disjoint set union, right? Uh, with a path compression to solve the problem, right? Or this one, what do we call union find to solve this particular problem. So let's discuss the key idea first. DSU with the complements, right? So we'll be going with the DSU with the complements. So first what we'll do, we'll represent each city X. So each city is this one X will represent each city X with a two nodes. Each city, suppose this one X, we will be representing this one with a two nodes in the DSU, right? X for placing city and X in the group A, right? X for placing city X in the group A, and another one is X plus N, another one is X plus N, right? So meaning X plus N, meaning X is in the group B, right? X for placing city X in the group A, and X plus N meaning X plus N, this one, sorry, X meaning X is in the this one, what do we call, X plus meaning X is in the group B, right? So for the edge U comma V, two groups are there, right? Sorry, I mean edges we are considering, right? For the edge U comma V, we must enforce U and V to be in the different groups. What we need to do here, for the edge U and V, we must enforce U, the edge U to V, basically U and V to be in the different groups to avoid this edge being inside a particular group, right? Enforcing this one, enforcing edge U and V, this one in different groups is equivalent to unioning U with the V plus N, unioning U with V plus N, and also V plus V with the U plus N, right? So this is fine, I believe, easy. So if at any point find of U, so as I've said, we'll be going with a this one distant set union. If you don't know the algo, so we'll be going with the find and the union, right? So if at any point find of u is equivalent to the find of v, what we'll be doing in the find, basically find operation, so we will be going with a, we'll be finding the representative, or we'll be finding the parent of the x, right, within the find, if you know the algo, right? So if at any point find of u which is equivalent, if it is equivalent to the find of v, then we have a contradiction, then we have a contradiction at that point of time, right? So there is no way to put u and v into the different groups. As we have the contradiction, there is no way to put u and v into the different groups. That means particularly the edge that we are considering, right, that must be internal, and so the hardness is at least this one, this edge's weight, the edge's particular weight, right? So the first time a contradiction happens, the current, this one edge's weight is the minimal possible hardness. So if we cannot partition, then we have to display the minimal possible hardness itself, right? If no contradiction after processing all the edges, then answer is -1. If we are able to partition the cities, then accordingly with the question we have to display -1. If no contradiction after processing all the edges, then we have to answer -1. If we are able to this one partition, then we have to go with the minimal possible hardness that we know how to do. That itself we discussed earlier, right? So this is fine, I believe. Now let's try to apply the same thing whatever we discussed in the we discussed theoretically in the form of this one for the on the example that they have given in the question, right? So first query in the sample, we are considering this one, first query in the sample, in the sense, just give me a second here. As I've said, what was the first query, basically this one, right? So this is the first query, 3, 5, right? 3, 5. So let me move on with the same here. Yeah. Now see here, we are considering 3, 5, and the edge indices are 3, 4, 5. Edge indices are 3, 4, 5. We have 3, 5 from 3 to 5 basically, right? Edge indices are 3, 4, and 5. So edges we have here is we have to consider earlier itself I have said. So this one basically edges 1 to 3 with the weight 38 they have given in the input itself. 2 to 1 we have been given 33, and 2 to 4 we have been given W weight equals 28. So what we will be doing here, we will sort descending by weight. We'll sort descending by weight, meaning here we will be going with the 38, 33, and 28 itself. Right. So 1 to 3, adjust 1 to 3, 2 to 1, and 2 to 4, 38, 33, and 28, descending order. Right. So this is fine. Now, first, what we will do, we'll add 38. We will add 38. When we have added 38, no contradiction. Right. So accordingly, with the theory that we have discussed, right. So next we will add 33. Then also no contradiction. We'll add 28. No contradiction. Right. So we have added all the weights here 38, 33, and 28. So no contradiction is found. In this case, what we have to return uh, as per the this one as per we had discussed earlier, right? So this one, when no contradiction, we have to return answer -1, right? So next, let's consider the second query, man. Now we have 2, 6. If we consider this one, we have got this one -1. Now we have the idea how we got -1 because there was no contradiction on the weights that they have given W. Now we consider 2, 6. So we'll get 33. So we don't have to discuss this one. So this is same, right? So for the 1, 3, 2, 3, and 1, 6, we already have the idea how we got -1. So -1, we don't have to discuss this one. We'll if we discuss this one 2, 6 for the query 2, 6, we'll be getting 33. So we don't have to discuss for other edges as well, right? So now let's consider query L equals to R equals to 6, right? Left 2, right 6 actually. The set includes a heavier edge of the weight 40, right? So this one we have to consider this one L equals to R equal to this one. Heavier edge, the set includes basically what it includes a heavier edge of weight 40 during the descending insertions. The edge weight 33 creates the first contradiction here. In this case, the edge weight 33, so we will be going with a 40, 38, 33, 28, right? So the edge 33, this one creates the first contradiction, right? So the answer here is 33. The answer is 33. So we will be going with a 33 in that case. So for the next, this one, two edges, we'll be getting -1 itself. No contradictions. And for the last one, 31. You can just try it out in the same way that I showed, right? For the first two, for the next three queries actually, right? So the output that we got here is -1, 33, -1, -1, and 33, right? So which is equivalent to the output that they have mentioned in the approach, right? Which is equivalent to the output that they have mentioned in the example one, mentioned for the example one within the question, right? So our approach works absolutely correct. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to big of m log m plus q log m into k. So why it is m log m plus q log m into k basically? So see, uh, building the segment. So we will be going with the segment tree as well along with the DSU, right? So building the segment tree and merging the list take roughly because m log m plus q log m into k, right? So where k is nothing but a small amortized this one, what do we call size of the compact edge list per node that we are considering. And practically we can just go with big of m plus q log m, right? Just for the constraints that they have given in the question, we can just go with big of m plus q logarithmic m, right? So what would be here? You can just consider this one as well, no worries, right? So what would be the space complexity here? Space complexity would lead to big of m plus n plus segment tree lists actually. With for the segment tree list, we can just consider extra variable as well, right? So we can just write it in this way, big of m plus n plus extra as well. So this is fine as well. So let's consider segment tree of list, right? So this one, but this is bounded by roughly big of m log m, right? So in the worst case storage of all the nodes, node list that we are considering, right? So this is fine, I believe. So overall space complexity, time complexity, and the space complexity would lead to big of m log m plus q log m into k and big of m plus n plus segment tree list respectively. right? So as we are completely familiar with the complexities and the this one, what do we call approach? Now we are good to write the code. Let's start writing the code. So let's start writing the code. So we'll be going with the DSU along with the segment tree, right? So this is going to be, the code is going to be huge, man. So first let's go with the constants and the global arrays. Before going that, so before moving on with that one, actually, we have to import input output package as well as the utility package, right? So we'll be making use of the fast input and the output along with the different utilities. So I'll just go with java.input output.star here, and also let me go with java dot util dot star. This is fine. Let me go with here public class. Yeah, this C has to be small actually. Class main. So this is fine. So within the main method, first let's go with the constants and the global array sizes, right? Same as this one, original actually. So I'll just go with here static final int. So let me go with maxim equals 2005. Next, let's initialize nodes, edges, queries, index along with a resulting variable, right? Anything it may be res or the ans, anything we can consider. So let me go with here static. So this one will be int n m. Let me give here q. Let me go with the index as well. Let me go with answer. This is fine. The next step would be let's go with a DSU parent array, nothing but the disjoint set union parent array for up to 2 into n nodes, right? So I'll just give here static. So this one will be int. So this one will be f equals new int of this one max n left shift 1 plus let me go with the 10. So let me do one thing here. Mm, yeah. So now I'll just go with the parenthesis here. Let me close the parenthesis here and close the array here. This is fine. Yeah. Now let's do one thing. Yeah, let's go with the coordinates for the compression as we are making use of the disjoint set union, right? So within the find, we'll be going with the coordinate compression. So this one static, let me go with the static here. Int, we have given, let me consider L. So new int of size maxim, right? So this is fine. Also, let me go with right as well along with the left. So this one will be new int of maxn as well. Simple. Yeah. Now let's go with the, as I've said, let's go with the coordinates for the compression. So this one was not coordinate compression. This one L and R, we are considering this one query left and right. Sorry. Yeah. This one. Now let's go with the coordinates for the compression. So this one will be, let me go with static here int. Mm, we go with a compression q. So this one will be new int of, let me go with maxim left shift 1, left shift 1. So this is fine. This is fine. Go with less than. Yep. Now let's do one thing. Let's go with a this one. What do we call edges? So this one will be static. So this one will be edge e equals new. So this one will be edge of 5 4 times 0 followed by the 5. So this is fine. Yeah. Now let's go with the segment tree nodes. When I say segment tree nodes, so here each stores a this one compact list of edges, right? So we can just go with the array list man for this. I believe this works actually. Let's go with the array list. 1 second. Yeah, let's go with the array list itself. Static array list here. So let me pass edge here. This is fine. Capital T variable new array list. So this will be maxim left shift 3. So this is fine. The next one will be static. So again, array list here. Let me pass edge. This is fine. Yeah, I'll just go with v equals new array list. right? So let me complete the syntax here. This is fine. Next, let's go with a simple edge container, right? So let's go with a simple edge container. So this one, let me go with static class edge. This is fine. So within this class, let me go with int u comma v edges basically w weight. This is fine. Now let's move on with the constructor part. So this one will be edge. So what we need to pass here? What are the things that we have considered? Int u edge basically int v along with a weight w. This is fine. Now let's go with the constructor part. Let me assign u to this one. What do we call? v, and finally this dot w equals. So this is fine. Yeah. Now let's move on with the further things. We are done with the edge class. Now let's go with the find with the path compression, right? So we are making use of the distance set union or the union find. So we'll be going with the path compression within the find method, right? So recently we have discussed about the this one. What do we call a distance set union algorithm or the union find algorithm? If you don't know the union find algorithm, you can just go through the important graph play this one graph algorithms playlist. You'll get the union find. You can just watch the video and you can just come here. It's very easy to understand, man. Yeah, I insist you to go and watch the algorithm so you'll get to know what we are doing very easily, right? So this is fine. Next, let's move on with a find with a path compression. Find method with a path compression basically. So this one will be static int find. So this will be int x. Yeah, let me go with return. So here if f of x equivalent to x, then let's go with the x. Else, let me go with f of x here, uh, which is equivalent to find of. So we have to just find the this one, right? Representative or the parent of x, basically f of x equals find of f of x. We have to give here, if I'm not wrong. This is fine. Find of f of x we have to give, right? So this one I missed this one somewhere. So this one, let me give parenthesis over here. Find of f of x. So this one, let me go with one more. This one parenthesis. So this one, yeah, one more parenthesis here. This is fine, man. Yeah, so let me come out of this one entirely. This is it for the find method. Now, let's go with the helper method just to initialize the this one distance set union nodes or the DSU nodes for the particular original vertex V, right? So let me name this one as init node, right? I'll just go with static here. So void init node. So this one, let me go with int x. Here, within this, let me go with f of x if it is equivalent to the x actually. Yeah. Let me assign this one to the x, sorry. So f of accordingly with the question, we went with the x plus n, right? X plus n, if you remember the next one, within the two criteria. So f of n plus x, let me assign this one to the n plus x, right? So this is fine, I believe. Next step. So we are done with this method, I believe. We are done with this method. Let me come out of this one entirely. Now, after the helper method to initialize the DSU nodes for a particular original vertex, so let's do one thing. Let's go with a solution, right? Solution method. So this we are just attempting to insert the uh, ed edge ed into the current DSU state. That's what. Let's do the same thing within the solution helper method. So I'll just go with here static int solution. This one I'll just go with edge ed. So this is fine. So within the edge ed, this one solution helper method, first let's go with the current representation, nothing but int u equals find of this one ed dot u. This is fine. Dot u comma v equals find of this one ed dot v. This is fine. Yeah. Now let's go with a if condition. Why? Because we have to go with a contradiction, right? When I say contradiction, if suppose we have to consider this one u and v are already in the same set, right? Then we cannot force them to be different, right? This itself is the main thing within the approach that we considered. We are going with a contradiction. Suppose u and v already are in the same set, then we cannot force them to be different, right? So I can just write it in this way. If u equivalent to v, then what we'll be doing, let's return -1. This is fine. So what if already forced to be different? What if already forced to be different? Then u in the A implies v in the B. So here we don't have to change anything in that case, right? For that also, let's write the simple if condition. So this one will be if find of u plus n here. So if it is equivalent to v, then we don't have to return anything. Let's return 0. Let's return 0, right? So this is fine, man. Now let's do one thing. Let's enforce u and v to be different by linking the complement. So we have to link the component u to v, and we have to link the component v to u, right? So this one I can just write it in this way. F of find of u plus n. This is fine. Let's assign this one to the v. Let me copy the same thing, or yeah, let me copy the same thing here. Yeah, let me paste it over here. So instead of this one u plus n, I'll just go with the v plus n. Let me assign this one to the u. We are successful in linking the component u to v as well as linking component v to u, right? Now let's go with the successful enforcement, nothing but in that case we have to return 1. Yeah, we are done with this part. Let me come out of this one entirely. Now let's do one thing. Let's merge two lists of the edges x and y into the v, right? Keeping only edges that are relevant for the DSU, that are relevant for the DSU contradiction detection. So this is the very important, this one. Basically, this is going to be the very important step, right? So let's make use of the helper method. Merge, basically. Within the merge method, what we are going to do, so the merge process edges will be there, right? From the highest weight to lowest. So we need to know the heaviest edge that causes the contradiction here. That is why, that is the reason we'll be going with the merge method here, right? So let me go with here static void merge. So this one array list. So this is fine. So let me pass edge here. Yeah, edge. Now let me go with array list. Let me go with the array list. Let me go with edge again. So this is fine. And finally, let me go with the list. Let me go with edge here. This is fine. Why basically? Yep. Let's do one thing. Let's initialize the DSU nodes or the disjoint set union nodes for all the endpoints we will touch. So let's go with a two for loops here. So this one edge, let me consider ed of x. So we have to consider for x and y both. Let me go with here. We have already written the init method if you remember, right? So I'll just go with here init node edge dot u. This is fine. So what we need to do here, one more thing. Let's make use of the init node again here. Init node. So this one has to be the same thing. Edge dot v instead of u, we have to go with the edge, right? So this is fine, man. So let's go with the y as well. So let me copy the same thing here. Let me paste it over here. So this one instead of x, I'll just give y, and here this remains same, right? So this remains same. The only difference is we are going with a this one. We are considering individual edges of the y actually instead of the x. This is fine. Now let me come out of this one entirely. Now what we will do? So let's go with a state that is returned by the solution. Initially, let's set s equals 0, nothing but the state to 0. And also let's go with a merge list that we will keep. For that one, I'll just go with the array list here. Array list of edge. So this is fine. Let me go with merged. Merged equals new array list. So this is fine as well. Yeah. Now let me go with int IA equals 0 and IB equals 0 as well. Right, so now let's do one thing. Let's merge by decreasing the weight. So we pick the larger W first, right? So I'll just go with a while loop here. While IA less than X dot size, this is also fine here. Or let's go with IB less than Y dot size. This is fine. Y dot size. And S greater than or equal to 0, then let me go with edge. Now this is fine. Yep, now let's pick the next highest weight edge from X or Y. Both list assumes sorting descending, right? So this one I can just write it in this way. If IA less than X dot size here and IB is equivalent to Y dot size here, or can just go with a X dot get here of IA. This is fine. Dot W, if it is greater than Y dot get here of IB dot W, this is fine. Now let's do one thing. Let me assign now equals. So this is fine. Now we will be assigning this one to X dot get of. So this one IA plus plus, right? So let me move on with the further things, right? Let's move on with the further things. So now, else what we will do here? Else, let me go with now equals this one. Y dot get of this one IB plus plus. Let me increment this one. This is fine. Yeah, let's try to insert this edge into the DSU. So I'll just give here S equals solution of now. So this is fine. Yeah, now let's write the simple if condition. If S not equal to 0, then let me go with merged. Let me go with merged here. Dot add of now. Dot add of now. Right, so let me come out of this one entirely. Now, what if S is less than 0? It means that we had a contradiction. When we had a contradiction, then the last merged edge is the heaviest that is causing the contradiction, right? So, resulting variable we have considered answer here. So I can just write it in this way. If answer, what if S is less than 0? Then let's go with a merge dot get here of merge dot size minus 1. So this is fine. Dot W, right? Else we are going to display minus 1, right? So this one minus 1. So this one, let me close this one over here and let me remove the parenthesis. Yeah, man. This is fine. Now let me go with V dot clear. After clearing, let's do one thing. Let me make use of add all operation here. Along with this, let me pass the merged here, right? So let's put merged result into the V, right? So this is fine, man. Yep. Let me come out of this one entirely. Now let's do one thing. Let's build the segment tree storing for each node a compact list of edges that are relevant for any this one query covering that particular node, right? So let's go with a build. So I'll just paste this one, build and the query, build query as well as the unique coordinates and the lower bound. This is purely related to the segment tree. Just give me a second here. So let me come here. Yeah, let me paste it over. Yeah, right. So this is fine. So I'll just explain what we have done here basically from the build. So within the build, why we are making use of the build here basically, right? So we are building the segment tree that stores for each node a compact list of edges that are relevant for any this thing. What do you call? Mm, that are relevant for any query that is covering that particular node, right? So we can put it in this way, right? So that is the reason we'll be going with a build method. So within the build method, first I have given t of p equals new RLS. So this one is nothing but we are initializing the nodes vector here. This one, line number 68. This is fine. Next, we are moving on with the further things, right? So we know the segment tree, man. By this time, we have already solved hell number of problems, right? Uh, so we have solved n number of problems. So this one, if q of l, whatever we have written, that is greater than m, we are just exiting, right? So if no edges is in this particular leaf interval, then we have to exit from there. Then we have made use of the array list here, this one, line number 71. So this one, after this, basically we have to consider this one, basically for loop, whatever we have done. So we have to consider edges with the indices q of L to Q of L plus 1 minus 1 that belongs to this particular interval, right? Then we are making use of the sort here. Then we are making use of the sort here within the line number 73. We are sorting based on the descending order, right? By weight. So this one we had discussed multiple times within the approach. So merge works by picking the heaviest first, right? So that is the reason we are sorting. Then merge of this one t of p comma t of p comma temp, whatever we have written. So we are merging into t of p, and t of p initially will be empty, right? So then we are gonna exit from here. We are gonna exit from here, right? So this is about the build method. So what is this query method then? What is this query method then? Give me a second here. So this mid is this is purely segmentary, man. This is fine. Yeah. So let me explain this one as well if you didn't understand. So this we are building the left child actually. So we are calculating the mid. You can just go with L plus R by 2, or you can just make use of the right shift 1 as well. It doesn't matter. So I can just write it in any way. So this is fancy way of writing, and this is also for the optimization purpose, right? We are making use of the right shift. We are going with a bit manipulation basically, right? So simple optimizations you have to keep in mind. Next one, we have made use of build twice actually. We are building the left child, line number 78, the line number 79, we are building the right child. Finally, here within the in the line number 80, we are merging the children's compact lists into the into what basically into parent, right? So we are merging children's compact list into the parent. So this is fine. Now let me come out of this one. Let's go with a query. Within the query, what we are doing, we are just collecting the relevant edge list for the query range LT to RT, nothing but left tree to the right tree by merging the segment tree nodes into the vertex V, right? So this is fine. Let's come to the query part, man. So what we are doing here, we have written the if condition right here. If LT less than or equal to 1 second. Yeah, this one, sorry. If LT less than or equal to 1, this one L, and R less than or equal to RT. So this one, this node is fully covered here, right? So what we need to do in that case, we have to merge its list into the vertex B, right? So that's what we need to do. Then further, it's pure segmentary. You can just look into it, right? So we have the idea. Now let's move on with the next method, unique coordinates, right? So unique CORDS, whatever I have written. So we are just compressing and duplicating the coordinates stored in the array, right? So this is one based data in this particular code, right? So don't get confused here. Now arrays.sort, whatever I have used here in the line number 92. So this one we are sorting the coordinates. We are sorting the coordinates here. Now let's move on with the for loop here. This one. So this, what it does, it keeps the unique values in the front. This keeps the unique values in the front. And finally, we are returning j here. So what does returning j say here? We are just going with a number of unique coordinates, right? We are just going with a number of unique coordinates, or it returns the count of unique values, right? So this is fine. Next, finally, let me delete this one. Finally, we are going with a lower bound. So lower bound, we have the idea on the upper bound and the lower bound. We have already done this one, right? Lower bound equivalent. So this returns the smallest index in this one. From this one, a of L to R, nothing but the left to right with the a of index greater than or equivalent to the x, right? So within the lower bound function, whatever lower bound helper method we are going with. So while left is less than right, this one, while L less than R, left is less than right, then we are calculating the mid. This is easy, man. We know this one, right? So this is fine. Let's move on with the further things, right? So we are done with the segment tree, this one, right? So we are going with lower bound unique coordinates query as well as the build, right? So this is purely related to the this one merge solution, this one find init node. So this one find and all, this is related to the DSU, right? So we know this. So this is nothing but the initialization part, right? So this is nothing but the pure initialization part. Now let's do one thing. Let's move on with the main method. So I'll just go with main here. Yeah, let me delete this one. Let me give throws exception. So within the main method, the first thing, so let me paste this one. What do we call? All the things that are related to the input output, so that we can move on with the this one logical part, right? So just give me a second here. So let me do one thing here. Just give me a second. Yeah, I'll just paste this one over here, right? So we are just going with a buffered reader and the print writer, fast input and the fast output. A string tokenizer to read the first line, NMQ. So we have been given NMQ in the this one, right? So this one we are considering NM and the queries, right? So number of nodes, Q queries, as well as the this one M, and number of queries actually 5, right? So 3, 5, 2, 6, 1, 3, 2, 6, and 1, 4, right? So this is fine, man. Yeah. Now we are done with this part. Let's move on with the further things, man. N, we know that number of cities. M, we know that a number of roads, nothing but the edges. Q is nothing but the number of queries. We know that one within the input, right? So we have already discussed this one. Let's move on with the further things. Now let me move on with the iteration for int I equals. mm I'll just go with, for int I equals 1, I less than or equal to m. So this will be I plus plus, right? So this will be I plus plus. Now let's go with a st, nothing but the string tokenizer equals new. Let me go with string tokenizer of buffered reader dot read line, buffered reader dot read line. So this is fine, I believe. Yeah. Now I'll just go with int u equals, let me go with integer dot %. So this is fine. % of string tokenizer dot. Let me go with the next token. Let me go with the next token. Yeah. Now let me go with b equals integer dot %. This is fine. String tokenizer dot next token. For this one as well, we are just going with uv as well as the w. Edges u and b, w is nothing but the weight, right? So b will be going with integer. Again, I should have copy pasted this one. Integer dot % of string tokenizer dot next token. Damn, bro, this is fine. So let me come to the next line now. So now we have to store the edge I, nothing but, so this is one based, right? So yeah, let me do that. E of I. So let me assign this one to the new edge of this one. We have to pass the vertices UV along with the weight. This is fine. Now let me come out of this one entirely. Now let's do one thing. Let me initialize Qi to 0. The next step would be, let's move on with a for loop, man. Yeah, let's move on with a for loop. So this one will be for and I equals 1, I less than or equal to Q. So let me go with I plus plus. So this is fine. So within the for loop, let me go with the instance of string tokenizer here. String tokenizer. So this one will be buffered reader dot read line. This is fine. Yeah. Now let's do one thing. Let me go with L of I. This is fine. This one will be integer dot %, integer dot % of string tokenizer dot next token. Right. So this is fine, man. Yeah. Now let's move on with the of I. So this one will be again. So let me copy the same thing. Let me copy and paste the same thing here. Copy this one and paste it over here. Right. So this is fine. Let me go with R of I. R of I. Yeah. Now let me go with Q plus QI. So this one, let me assign this one to the left of I. Right. The same thing. Let's do this one for the right one as well. So let me copy the same thing here and let me paste it over here. Instead of the left, let me go with the R here. This remains same, right? So let me come out of this one entirely. Now, So we have to get the number of unique coordinates, right? So let me initialize unique to this one. We have already written unique coordinates helper method, right? So this one, let me pass capital Q along with a QI, right? So this is fine. The next part is we have to go with the number of leaves equals unique one. In this case, let me assign the index to unique this one minus one, sorry, not the plus one. This is fine. Yeah, unique one, right? So unique minus one basically. Now we have written the segment tree, right? So we have written the segment tree, right? So we have already made use of the build helper method, right? So let's build the segment tree over the intervals. This one to idx, nothing but the index where interval I corresponds to the edges, right? So q of I comma q of I plus 1 minus 1, right? So now what shall we do? Let me go with here build of this one. What do we call 1 comma 1? Let me go with the index. So this is fine, I believe. Yeah. Now let's go with a for loop man for I equals 1 I less than what do we call I less than or equal to q I less plus, right? So this is fine. So let me go with v dot clear here, v dot clear here. This is fine. Now let's do one thing. Let's go with a find compressed index of L. Also, let's go with a find compressed index of R. Nothing but L of I and R of I minus 1. Right. So for that one, we have made use of the let's make use of the lower bound helper method. So I can just write it in this way. Int x equals. So we have already written lower bound helper method. You can just scroll top and you can just look into the code actually, right? So I'll just go with Q. What are the things that I need to pass here? One, let me go with unique here. Also L of I, right? So this is fine, man. Next, let's go with Y. So I'll just copy this one. Let me paste this one. Let me go with Y equals lower bound of. So this remains same. Nothing but in the case of L, we have to give R, and also we have to include one thing. This one. Instead of just R of I, we have to go with the R of I minus whole one. Actually, this is fine, man. Next thing, we have written the query helper method as well. So we have to gather why we have written that one, because we have to gather the relevant edges via merging the segment tree nodes into the vertex V. And we have to update the resulting variable ANS we have considered, right? So that one. So I'll just go with query here, a query of what are the things that we need to pass here. 1 comma 1 index comma this one x comma y. So this is fine. Yep. Now let's print the answer for this particular query. I'll just go with out dot println. So let me give here println of this one. Let me go with the answer, right? So this is fine. So let me come out of this one entirely. So this will be out dot flush of out dot flush, right? So this is fine. Yeah. Yeah, this is it for the code actually. This is it for the code. So before checking the code with the different inputs or the examples, let's do one thing. Let me copy paste the signature starter template. Just give me a second here. So let me paste this one. This is fine. Now let me come to the question. So I'll just copy this one. The output that we need to get here is minus 1, 33, minus 1 twice and 33 again. So let me check the same here. So unchecked conversion, this is fine. This is just the warning. Let's move on with the error part. So parse int, I have to give capital I here, line number 141. Where is this? 141. For both actually. So let me go with this one, capital I for this one as well. This is fine. Let me run this one again. Yeah, now we are getting the output minus 133, minus 1, minus 133. So this was the problem actually. The percent I had to give the capital I instead. I had given the small I, right? So all other things works absolutely correct. So we have discussed this one step by step along with the approach and the complexity before, right? So this is fine. Now let me do one thing. Let me copy the code entirely. I'll just come here. Let me hit the submit code button. So yeah, let me consider D from the drop down. So this is problem D itself, right? Dividing kingdom. Let me paste the code and let me hit the submit button. So let's wait for some time. Let's wait for some time. Just give me a second here. So let's wait for some time. So here we are getting the runtime error on 13, right? So what's the mistake? Let's check here. The output, what we have done. So for the big one, what output is it? Text 505 out of bounds for the length. This one we have considered 5 with this one itself, right? Yeah. It's around here. Just give me a second here. Array size we have considered this one. This is fine. Or oh yeah, we have to go with the 4 zeros. Man, yep, sorry. This one we are going accordingly with the constraints, right? So this is fine. Have to give. So that is the reason we are getting this one. So let's do one thing. Let me copy the same thing here, and I'll just come here. Let me submit the code again. So I'll just go with D. Let me paste the code and let me hit the submit button. Yeah, let's wait for some time actually. So this has to work now. Mm, so that is the reason we were getting runtime error, right? Let's wait for some time. If you know what I mean. Yeah. Now, yeah, this has to work. Let's see. So we have purely went with the this one, disjoint set union along with the this one union find along with the segmentary basically, right? To solve this particular problem. Mm. This implementation is quite difficult, man. Not quite difficult. It's intensely difficult. I'm not gonna lie. So it feels good when we are teaching or when you are teaching or this one after getting the things after knowing the things after what you teach for that one you'll feel very easy, but for the implementation if you're doing without internet or if you are doing without this one, what do you call, uh, Gen AI tools or without Google, if you're trying to implement it, this is intensely difficult. I'm not gonna lie. This is for the division one, right? This is extremely difficult one. So you can just try to implement, no doubt, but yeah, as I've said, without internet, without Google. So if you're trying to implement only with a question and answer, you're trying to write from the scratch, this is hella very difficult. You have to have the idea on all the algorithms, man. Most of the algorithms. So we are discussing the algorithms, this one parallelly, right? So we have discussed almost 60 plus algorithm currently. So previously, yesterday we had discussed on the Kosaraju's algorithm as well as the this one, I believe. Kruskal's and Prim's we have discussed already. Kosaraju's algorithm we are done with that. Now today we'll be discussing on the this one, I believe. What do you call? Kahan's algorithm along with the um, this one. Kahan's algorithm for the topological sorting along with the Kahan's algorithm. We'll be going with the Hungarian algorithm, I think. Yeah. Now, yeah, you can clearly see here the verdict that we got here is accepted, right? So whatever the code that we have written works absolutely correct for all the test cases, right? So we have went with the correct data structure. Right, this is fine, man. Yeah, now we are done with this particular problem. I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.